restart the stream. I can't talk anymore. And share the screen. There we go. Can you see two Word documents I've arranged? Okay, yeah, I've got the same file open twice so that I can compare and contrast across models. I thought that would be a little more useful than usual, but let me make one of these big for a second so that I can answer your question about getting data from wide format into long format. So just to review, this will tie pretty closely to your homework, although there's only two variables that you'll be working with. The original format is right here, where it's one row per person. So all of their separate outcome variables are stored in separate columns. The objective is to get to a data structure that looks like this, where it's one row per outcome per person. So there's one column here that I'm named at the very end, body rating outcome, that holds the information from all three of these outcomes here, the actual rating, the ideal rating, and the discrepancy between the two as the three different outcomes in this example. To keep track of which outcome is which, there is one index variable, which is this DV variable right here. And then I've created three different dummy codes that will act like the switches when these go into the model. So even though it seems redundant to have both a DV column and the dummy coded columns, they're used in different ways. The DV column is used as an index for the R matrix. It's more just like an ID variable, so to speak, whereas the dummy codes will actually go into the model. So how that happens, and Terry, since you're asking, you want to look at SAS is my guess, right? That work? Okay. And we can do Stata too if anyone wants. So the original data set is in the wide format. That is saved. I have it as a SAS format in this example. It's in a place called File Save, this is my path to your guys' class handouts. And the name of the original file is example 5A wide. So I imported that directly so that I could sort it to figure out where the men and women start so that I could get that information for printing our matrices per group later on. But here's where the actual stacking happens. So I'm bringing the original file that goes on set, and I'm pulling it from the permanent directory, and then what goes on data is the name of the to be created file. In theory, I think you could use the same name for both, but I've had stuff get screwed up by that before, and so I just make a new one. And since in SAS you can have as many files open as you want, it doesn't matter. So the new file is example 5A. And it's going to be in the work library, which is where all of the stuff that I'm actually working with goes. I centered predictors here. That happens prior to the stacking. So those new variables are going to be pasted down the rows across everyone's data. Then this part is where the stacking happens. The output makes it write a whole new line. So what it's doing is it's taking the line of data that you have, it is adding this information to it, and then writing it. And so then basically it's going to have 3 times as many rows because it's writing this 3 times. So the first row I have designated as the actual row. So I filled in, this is actually a string variable that I created. It's a lazy way of making a categorical variable that has value labels embedded in it. SAS lets you do that, so I'm lazy. It just saves a couple steps. The only catch is that the string variable by default, if you don't tell it how long it is, it holds the length for the first instance. And so it's advantageous that actual is the longest word here because otherwise it would truncate it. There's a length statement you can use if you want to solve that, but not necessary here. Note that I am putting the 1, the 2, and the 3 in here to keep them in the order in which I want them because otherwise it would go alphabetical and screw me all up. So we're creating 5 new columns in total. One of them is DV, 3 dummy coded columns, and then the outcome itself goes here. So this is like a generic column that holds all 3 outcomes simultaneously. And then the dummy codes turn on and off depending on which one you're talking about. And then just adding the labels. I dropped the original outcomes just because I didn't need them anymore, but it doesn't hurt anything if you leave them in. I was trying to literally come up with a data set that would fit on one page to make the handout, and it was too long otherwise. So that was the only reason I did that. This dropping of old multivariate variables happens automatically. And in Stata, you can't not do that. Like it automatically takes them away. There's no option to keep them unless you'd have to make a copy if you wanted to keep them in there. Okay, now does that help? Okay. Does anyone want to go over this in Stata as well? Molly does. Molly from the mountains. Molly's going camping, it looks like. Glacier National Park, excellent. Let me find Stata codes first. Okay. So I am importing the original wide format data, generating the centered predictors that are going to stay with it. Because the variables to be stacked do not have a numeric suffix, Stata kept yelling at me. I couldn't figure out how to work it otherwise, and so I gave up and decided just to rename them. So solely for the purpose of making Stata understand what I was trying to do with this reshape command, I renamed my 3 separate columns as rating 1, 2, 3. After I did that, it was able to create a new column called rating and then build a DV variable. So these are the names I'm giving it. So I called it rating, I called this DV, but what goes into J are the numbers that are attached to the names here. So if this was 456, then the DV would be 456. It's whatever numbers go with this. And then of course I had to change the capitalization so that the variable label looks nice to me. So if you had more than one column to be stacked, you would put them in here. So like if I had predictor 1, 2, 3, and I had outcome 1, 2, 3, then I would have another one here that's like predictor and then rating, and it would make extra ones. The analog to this in SAS is just making new variables within that same row where everything that goes together has to be before the same output statement. Okay, does that help, Molly? Do you have other questions? Okay. Anyone else have questions on stacking data? You'll get a chance to practice this in your homework for. And then, yeah, the dummy codes parts, I'm assuming you've seen before. The generating new variables and then setting them to 1 if these conditions are met for each DV. Other questions on that? Data stuff? Syntax? No? Okay. No. Okay. I'd say 4B or 5A. Yeah. In the instructions, I suggested 2 ways of coding it. I would suggest either using outcome-specific intercepts or group and outcome-specific intercepts. So the context is there's 2 training groups. They're either trained in making pancakes or making crepes, and then they're asked to make each dish. So you could, in theory, make 4 dummy codes for each unique combination of training and outcome and just put those in the model. Or you could make 2 dummy codes for which outcome is which, and then put in training group as a traditional predictor, as well as an interaction so that you've got different effects of training group on each outcome. I'm not sure which would be easier. The former, having DV-specific intercepts and then the effective group looks more normal, like what we're used to doing, but it's also potentially more confusing. I don't know. But if you get in the weeds, let me know and I can help you code it up. Or we can talk about coding schemes that would make it more or less useful. All right. Other questions or things you want to talk about? Did you hear it's going to snow tonight? Seriously. It was like a week ago when it was 80 degrees, and I remember thinking, well, at least we're not quarantined in the middle of winter. Never say famous last words, because they could be. All right. Then let me see which. I have two windows open here. I have the same file open twice so that we can compare across models because I thought that that would be easiest. Let me get to where I wanted to be inside this one here. Just one second. Doop. There we are. Okay. So what I wanted to sort of the big picture here, how I have a 24-page handout about four means. Oh, chat window. Hang on. Let me get over here. Where did it go? No snow in South Dakota. That's not fair. Snow in Iowa. Yeah, this is BS. No snow in Pennsylvania either. Ugh. Snow in Pennsylvania is a thing. I lived in Pennsylvania for 2 winters, and like the snow forecast would be delivered in feet. Like 2 feet of snow would drop overnight. It was crazy. Anywho, at least it's not going to be that. But all right. So where was I? I'm rambling again already. That's bad news when we're 13 minutes into class and I'm already rambling. 82 degrees in California. Yeah, Alfonso, just suck it. Okay, just we don't want to hear about that. Not cool. You guys, California has you guys have cleared the what is it, the curve already from all the reports, and you have 82 degrees. It is just simply not fair. Anywho, um, there are a lot of confusions, I would say, in how people think about difference scores and whether or not they should be predicted or how to do it. There's some shenanigans that some statisticians have pulled in the literature claiming that you can make like latent difference scores and they're somehow more perfect and special than regular difference scores. So, part of my motivation in making a 24-page handout here is to show you every possible way you could set this up and how they work out to be rearranged versions of the same idea. So, I have it within mixed as a multivariate model to start with. Part two of this visits the same idea in the world of path models, and that's where the shenanigans really begin. Um, so that's sort of the big picture is to show you all the different parameterizations and how they translate into each other. So am I frozen? Can you hear me? We're good? Good so far. All right. Um, there we go. So here's on the top of my screen here. Can you see the giant pink mouse? Okay, the giant pink mouse. It's a giant pink mouse to me. It's a small pink mouse to you. But yeah, well, it looks huge on. I have a 34-inch monitor that I'm staring at. It's like a television screen, so that's why. I got tired of losing my mouse, and so I made it big and pink. But up here in the top window, this is the model that we looked at last time. So just to remind you the story here, we are interested in predicting discrepancies between what people actually think their body looks like and what they think it ideally should look like. So the construct of interest is the difference between these ratings and whether or not that discrepancy varies by gender. So the first model we looked at last time is model 1A. It is an example of a DV-specific intercept model, and this is what I would recommend for your homework is this one, where beta 0 and beta 00, excuse me, and beta 01 are DV specific intercepts. So what I'm predicting is actual ratings and ideal ratings. I am then asking for a gender difference in the actual ratings and in the ideal ratings. So this setup maps directly onto the pancakes and crepes story in your homework. In terms of the notation, I'm using the subscripts IT So it's individual, and then T is for the outcome for each person. So the first subscript has to do with the order of the predictor for a person. So we're going to start at 0 no matter what, and then it's beta 1 because gender is the first predictor that I have for each of these. And then the second subscript indexes which outcome is which. So the second subscript ends in 0 for anything pertaining to actual, and the second subscript ends in 1 for anything pertaining to ideal. Notation is always author specific. This is actually backwards from what it looks like in multi-level models, but the reason that I chose to do it this way is because in multi-level multivariate, I always put the multivariate outcome last. And so I'm trying to be internally consistent across my own notation across classes. So rating is the generic column that has all three outcomes in it. Remember, we have actual, ideal, and I made a specific difference between the two of them. So in this first model here are the 4 fixed effects that correspond to the betas up above. And then I'm only using the rows in the data set that correspond to the actual outcomes and to the ideals. So this makes sure that the row that has to do with the differences is not included in the analysis because it would be redundant and screw things up. Now, down below is an alternative way of setting up the exact same model. So this is 2A that I'm contrasting it with. This is a general intercept version of the same model. So we're still predicting actual and ideal, but I've put the general intercept back in. So I've got beta 0, 0 sitting here by itself. So that means because actual is not in here anymore, that actual is my reference DV. So the beta 0, 0 is going to be the expected outcome when everything else is zeroed out. That will be the actual outcome, and it will be the actual outcome for men specifically. That's what beta 0, 0 is going to be in this model. So because everybody has a 1 to start off with, the intercept is going into everybody's score. All 3 fixed effects after it then have to be deviations of some kind relative to that reference point. So beta 0, 1, excuse me, for ideal here, that is not the intercept for ideal. What is it? I'm going to watch the chat window and see who logs in first with the answer, or you can just talk, whatever you prefer. So the question is, this beta 0, 1 down here for ideal, it is not the ideal intercept. What is it instead? Actual plus ideal. Not quite. Difference, yes. It is how ideal differs from actual. So that's kind of like, what? Like, why would you do that? And then if you think back to what the researchers wanted to know, this beta 0, 1, the difference of how ideal differs from actual, that is body discrepancy. Like, that is that idea in a fixed effect directly. How much bigger you think you should be or how much smaller you think you should be. Exactly. Yes, Jing, exactly. Oh, that's what you meant. Okay, well, you're both right then. I just misunderstood what you had said. So yeah, so that means then that we have a main effect of gender here, and we have an interaction of gender by ideal. So following the rules of interaction terms, this main effect of gender, beta 1, 0, who is or what is that the effect of gender for? So this main effect of gender, it's not a main effect, it's a simple main effect. This is the difference between men and women for what? Dot, dot, dot. Am I frozen? No? Okay. There's some answers. The chat window's frozen. Here, yes. It is the difference between men and women for what? Actual. There we go. Yes. The reference DV. Because the second one, when ideal is 0, we're talking about actual. So this main effective gender here, beta 1, 0, that is the effective gender specifically for the actual rating. Beta 1, 1 then is how the effective gender differs for ideal. Or you can say it another way, it is the effective gender on the discrepancy. Because this effective ideal right here is the discrepancy. This is the gender difference in discrepancy, that interaction term, beta 1, 1. Okay, are you with me so far? Now, what if I left out beta 1, 1? What if beta 1, 1 was gone? And I'm putting my hand up to cover it as if that's going to help. Here, let me see if I can, yeah, what if that was gone? There we go. How would that change how we would interpret beta 1, 0? And you can hit your spacebar to talk momentarily, I think. Just women. It's a gender difference. So it's not a mean for a woman per se. It's a gender difference between men and women. But for what kind of outcome? If the interaction term that's highlighted was not included, how does that change the interpretation of beta 1, 0? More generally, what does a main effect mean in a multivariate model? That's what I'm asking here. This is a specific case of it, but that's the sort of the more general question. No one wants to talk? Okay, I'll tell you. So this term right here is what we're talking about. If this wasn't here, it's just the effective gender period, right? It's marginal. Well, marginal in this case means across outcomes. So you would be saying that the effective gender is the same in predicting actual ratings as it is in predicting ideal ratings. The effective gender would be the same in predicting actual ratings as ideal ratings. That is actually a constraint. That is a testable hypothesis as to whether you need 2 effects of gender in the model or 1. No gender difference. It's saying that the gender difference is the same across outcomes, not that there's none. So the other way of looking at this interaction term is its job is to ensure that the model has a different gender effect for each outcome. This is how the effective gender differs if you're talking about ideal versus actual. So then to try and figure out how the model gives us all the pieces of information, try and make this a little bit bigger on the bottom here. The first 4 rows are the means for each condition. And so this looks a lot like what we're used to seeing in a 2x2 design, where you've got your intercept, you've got the main effect of one dimension, the main effect of the other dimension, and then the interaction term. The gender difference then is given directly for the model for actual. And if you want to know what the gender difference would be for ideal, you have to start with the gender difference for actual and add to it the interaction term that allows the gender difference to differ between ideal and actual. In terms of the discrepancies, that is captured directly by the effect of ideal in this model, given the use of the general intercept. So the main effect of ideal is enough if you're talking about the discrepancy for men. To get to the discrepancy for women, it's what is the discrepancy for men plus how it differs for women. And so then this thing right here is the answer to the research question. Is there a gender difference in discrepancy? That is the interaction term. So last time in the last quiz that we did, one of the things we were talking about is in terms of strategy, like which of these ways of setting things up works better or worse. If what you want to know is a difference between outcomes, such as in this case, body discrepancy, setting it up so that the difference between outcomes is a fixed effect is going to give you a more direct answer to what you want to know. And I just noticed that this isn't green for whatever reason, and that's going to bother me, so I'm going to fix it. Did you guys know that I actually color all the syntax for Stata myself? True story. I figured out a hack using HTML for some of it, but it doesn't work for comments. And so I actually manually go in and I green these all for you. I don't know whether that is impressively anal or just impressively dedicated, but I green all these things for you. So that's why sometimes they get missed. It's dedication. Thank you. I just feel like the code is so much easier to read when it's in the right colors. Once you get used to seeing the colors, like it really helps shape like your attention and guide you towards what you should be looking at. So I commit to the colors. But anywho, so if we roll through the results, make this big here. There's the SAS version of the same stuff. Model fits the same. Model variance components are the same. Now we get DVI is the discrepancy, is the difference between outcomes specifically for men, how that differs for women. The research question is given directly by the fixed effects, and then you can get all the other fixed effects here as well. Okay, how are we doing so far? Okay, so just to review, first model we looked at predicted actual and ideal using intercepts for each. To get to what the difference between actual and ideal is, you had to write lincoms and to subtract one from the other. That was 1A. 2A here is equivalent. It has the same number of parameters, same fit, same everything, but it uses a general intercept so that the difference between outcomes is in the model directly as a fixed effect, not as a linear combination. What it means, though, is to get to anything related to ideal, those are all linear combinations. Because the model tells you what it is for actual, it tells you how it differs for ideal. And you have to add those together to get to whatever it is for ideal in terms of an intercept, a gender effect, etc. Let me show you one more, actually not one more variant, lots more variants. The next variant. This one is for reviewer 3. This is going out to you, reviewer 3, who made this handout possible. I'm going to put in the difference now as an outcome. I'm going to predict a difference score. So do you remember how at the very beginning I had stacked up my 3 outcomes? So I had actual, ideal. I created a column that is the difference as an outcome variable, even though that's redundant, and I stacked it in here. Well, I'm going to predict the difference directly. Oh, come back. Too far. Too far. Scrolling, scrolling, scrolling. Almost. One more. Here it is. Is this where I was? Yeah, 3A. So I'm going back to DV-specific intercepts, and I am predicting actual, and I am predicting the difference. So here's actual, here's the difference, here's the gender effect on each, and now I'm kicking out the outcomes for ideal because they would be redundant. So to get to this, let me see here. Can you guys see this? Is this big enough? Okay, I'll try and make it as big as I can. And the scaling here is a little different. So what is that? Go up to the equation too. In this context, what's that? What's beta 0, 0? Watching the chat window eagerly. What is that? Intercept for actual. Correct. What's that? Yes, difference between ideal and actual. Correct, everybody. Yeah, it's the exact same model that I just fit with a different parameterization. I put in the different scores as the outcome rather than tricking the model into making them for me. So now we have a gender effect specifically for each of these outcomes. Beta 1, 0, it gives us the gender effect for actual. Beta 1, 1 gives us the gender effect for the difference. Now, what if I wanted to predict the gender effect for ideal? Can I still do that, or am I shit out of luck? You can still do it? Question mark. Math. Yes. Linear combinations. Yep. If I know actual and I know the difference, I can get to ideal. And if there's ever a doubt that I can do it, all you got to do is look down at the code and see if it's there. Here it is. Actual plus difference gives me ideal. The gender difference on the discrepancy, again, is directly given as a model parameter here. So if you predict the difference as an outcome, you can still use DV-specific intercepts to do that. Now, what would happen, do you think, if I decided to try and predict all three simultaneously? Put all three outcomes in: actual column, ideal column, difference column. What do you think? Could I do that or no? It doesn't work that way. Terry thinks we can. I tell you what, I tried. You can't. Because one is a linear combination of the others. It's redundant. Yep, exactly. So for the same reason that I can get to ideal if I have actual no difference, I can't put ideal in the model. And I had another story, another reviewer story. You know, it's not a coincidence that I talk about pleasing reviewers all the time, is because this has been my life. You know, I have like 70 papers or something, and not a one of them did I not have to fight with a reviewer on. But I helped a graduate student set up a model similar to this, where she was interested in how people did, like there was like a baseline condition and then a after something happened condition, and she was interested in predicting the difference between the two. And so, since that's what she wanted to know, I instructed her to make a difference and predict that in the model as well as one of the other outcomes. And I think I had her do the baseline one. So we predicted baseline performance and difference in performance across these conditions. And reviewer three is like, well, you can't just put the difference in. That's why you need to put the other one in too. No, you can't. It's redundant. The other one is in there because the two of them added together get to be the third. So this is to say there's three things that you might want to know here in a multivariate model that has two outcomes. How stuff predicts outcome one, how stuff predicts outcome two, and how stuff predicts the difference. Given any two of those, you can get to the third. The only thing that makes this instance a little bit different than the others is what you get with respect to your variance components. So I hadn't been paying much attention to those and describing this for you, so let me back up and look at those. So if we're predicting actual and ideal, here's the R matrix that we get. Where R matrix is the variance covariance matrix of the residuals across outcomes for the same person. So they're in order of dV here. So actual is first. So this number is the residual variance after controlling for gender of the actual ratings. This number is the residual variance after controlling for gender of the ideal ratings. And this is the covariance between actual and ideal, which works out to be a correlation of 0.92. So long as what you're predicting is actual and ideal, whether or not you do that with one intercept or multiple intercepts, your variance components are the same because you're predicting those two outcomes. If we switch to predicting the difference directly, like what we just did, then that's the variance that you're going to get back. So the R matrix then here, it's the same residual variance. Stop it. It's the same residual variance for actual here, but this is the variance of the difference scores. It's a different number. It's not the variance of ideal, it's the variance of the difference scores. And here is the correlation between the actual and the difference scores. So if you change which outcome is being predicted in terms of which row, the variance and covariances you get back change along with that, but they're still linear combinations of each other, so it's still the same model. So you'd have to decide in setting this up when you want to talk about, say, R square for your model. Do you want to talk about how well the model predicts actual ratings and ideal ratings, or do you want to talk about how well the model predicts the discrepancy? If you want to talk about how well the model predicts the discrepancy, then discrepancy should be the outcome variable. That way you get the variance components for it yourself. So I had fit a second model here where I let the variance covariance matrix be different by gender. We find that one here. That's the next one because I hadn't yet tested whether or not the variance of the difference scores needed to vary by gender. I lost it. It should be here somewhere. I don't know. Maybe I didn't do that. I thought I did that. Maybe I actually left one out. Last but not least, here's a model that predicts difference scores directly. This is what my colleague whose data these are did that set off reviewer 3. What do you think is going to happen? Are my answers regarding body discrepancy going to be any different than they had been in any of the other models just by putting one outcome in instead of two? Nope. So this is a univariate model. The answer that we're looking for, the gender difference was minus 0.806. It's been the same number this entire time. If I just predict the differences in a univariate model, there it is. Same standard error too. So yeah, there's actually nothing wrong with predicting different scores. The only thing that would be potentially wrong is if you're missing out on some information. So if all you knew is that there's a gender difference in discrepancy, you don't know why there's a gender difference in discrepancy. The gender difference could have resulted because the women were actually heavier on average than the men, but they agreed on what ideal should be. It could result because men and women were actually about the same size, but they differed in what they thought ideal should be, or some combination of both, right? So the problem with different scores isn't mathematical. It's interpretive, it's conceptual. So the rationale for putting in actual and a different score, or actual and ideal, is so that you can answer all three questions simultaneously to try and nail down what is the source of the difference. And based on what we've found in the previous models, let's back up to any one of them because they're all going to tell us the same thing. There was no significant difference between men and women for actual, but there was a significant difference for ideal. The women thought they should be more smaller than the men, and that's what created the gender difference in body discrepancy. So the rationale for putting at least one of the outcomes in with the different score is that it helps you isolate the source of why things are predicting the difference significantly. Is it a difference in the first outcome, the second, or both? All right. Let me see where I'm at here. Oh, here's the one I lost. Yeah, different residual variance. Oh, this is what I wanted to show you. This is what I was just looking for. I knew I had it in here. I just couldn't remember why. Um, yeah, this is what happens when you make a 24-page handout. Okay, I forgot. the I'm on page 9. That's where I am. Because I wanted to show you one thing that I hadn't gotten to show you all semester, and I was trying to figure out where to put it in. It is like Where's Waldo? Yeah, but this is my overzealous handout on different scores. I didn't get a chance to yet test whether or not the residual variance should differ between groups with respect to the difference score. And I decided to do that in the univariate model so that I could get at just that one parameter directly. And I wanted to show you this code because, at least in SAS, you can do some more general variance hypothesis testing. So the way that you can do this in Stata is this by statement right here. You can allow your residual variance to differ by groups, but I could not figure out, within Stata mixed at least, how to tell it to let the residual variance differ as a function of any kind of predictor. But I do know how to do that in SAS, and it's right here. This is a new option that you haven't seen before on the repeated line. It's the local option, exp for exponentiate, and then I'm putting in my gender predictor. So the model that's being fit, in addition to the regular model that has the fixed effects, this is called more generally a model for the variance. What I am doing is saying that the amount of variance that's left over can differ as a function of predictors too. Because variance can't go negative, the model actually predicts the log of the variance instead of the variance itself. That way, when you exponentiate to get back to regular variance, that variance estimate stays positive. So if you're in a situation where you have non-constant variance in a general linear model, it looks like the variance increases because it's supposed to be constant, right? Am I frozen? No? Okay. You're still listening, right? We're still hanging in there in this very exciting Zoom classroom. Thank you, Terry. Yellow thumbs up from Terry. We have, this is a log linear model for the variance. This is allowing hypothesis tests about variability. So you can test whether or not the remaining variability in a model itself differs as a function of predictors. So that's the last thing that we hadn't really talked about with respect to the assumptions of general linear models, right? You're saying that your residuals are normal, that they have constant variance, and that they're independent. Well, we learned how to fix if they're not normal. If you pick another distribution, most of the other distributions don't assume constant variance. But if normal is still plausible, but you have some sort of like fan pattern to your residuals, you can allow the variance to grow as a function of the regression line by putting predictors into your linear model. So I wanted to show you how to do that because it's one of those things that you may run into. And sometimes people have hypotheses about variance as well as means. But the output for that, the way that you would interpret this is that, and then this parameter right here tells you the difference in the log variance between men and women. It's non-significant, so that means we don't need to have the variance differ as a function of gender, but what it would mean is that the women have less variability in their difference scores because the coefficient is negative. So in the context of multi-level models, these are known as location scale models. You can allow your random effect variances and your residual variances to differ as a function of predictors. It's a new area. I'm frozen. I froze a little. How does one freeze a little? Okay, where did I get frozen at? Starting from residual. Okay. So, okay, we'll back up then. So what we're doing is, in addition to fitting a model that has fixed effects to predict the difference score, that the mean difference score differs by gender, what we're also doing simultaneously is a variance model in which the residual variance gets to differ by gender too. The way that I'm doing it generalizes not just to grouping variables as predictors of differences of variance, but also quantitative predictors or interaction terms. It is a linear model predicting the variance amount. So it is a model that predicts heteroskedasticity with predictors. That's what we're doing. With me? So hang on here. Let me get out Paint for a second. You guys remember Paint? I haven't pulled out Paint in a while. Here we go. Welcome back to Paint. I need the spray can. Here it is. I'm going to make my residuals blue. Spray can. See, it's fun. Okay, let me back up here. I need a paintbrush. So if I have, here's my regression line, right? It's a little bendy. I'm sorry, I'm a shitty drawer. And if I have my residuals, let me get my spray can out. My residuals around the line should be like pretty much even, right? So this is my best shot at homoskedasticity via Paint. Now, what if instead the residual variance was actually larger for people who have higher values of the predictor. So you see like this sort of fan spread of the residuals out here, right? So there's more heterogeneity around the regression line the higher the regression line goes. Well, if that's the case, then what you need is to be able to tell the model that sigma squared E, the amount of residual variance, also needs to increase. So it would be like you're building in that fan shape pattern into the model. The way that you can do that is this local option in SAS. I looked for it in Stata and I couldn't find it. I'm sure it exists somehow. You may have to write one of the ML like custom algorithm thingies to make it happen, but you can put in other predictors into this model. So this man versus woman happens to be a dummy code in this example, but it could be a quantitative predictor. You can have more than one quantitative predictor, and you can have interaction terms or any of that. So it's a model that predicts why the heteroscedasticity is there. So it changes it from just like a broken assumption to something that you would want to know. Like, why doesn't the model work as well at certain values of predictors? That would be the type of question. Okay. Did I freeze in any of that, or are we good? Okay, we're caught up somehow. Okay. So the model for the variance then is telling us that the amount of residual variability is smaller in women, but not significantly so. So it looks like they can share a coefficient. All right. How are we doing? Okay. So here's some other stuff that we haven't even talked about. Up to this point, we've considered actual and ideal as outcomes only, but they could also be predictors. Maybe body discrepancy is higher for people who are bigger to start with, or for people who think the ideal body should be smaller. So to what extent does your actual rating predict your body discrepancy? Or what extent does your ideal rating predict your body discrepancy? We can put those outcomes into a univariate model as predictors instead. So I did that in two subsequent models here. This is 5A on page 9. This is a linear model predicting only the difference score. And now I'm using actual as a predictor instead. I centered it at 4, which was near the mean-ish middle point of that scale. And I'm asking whether actual ratings predict body discrepancy and whether they do so differently for men versus women. So there's only 3 things really that I want to know. What is the slope for how actual predicts differences in men? What is it in women? And do those actual slopes differ? Survey says actual does predict the difference. People who think their actual body is larger think that their difference should be smaller. They think that their ideal should be smaller. The difference is more negative. However, that tendency does not vary between genders. We can do the same thing for ideal, where I put in ideal here instead of actual. Could I put a model together where I have both actual and ideal predicting the difference simultaneously? Nope, it's redundant. Again, linear combination can't have all 3 of them. let's see if ideal predicts different scores. Yes. The larger your ideal body is, then the more different it is, the discrepancy is. But that's the same for men and women. So what are we missing then potentially in treating actual and or ideal as predictors? We don't get to know if there's gender differences in them. So this is a situation in which multivariate models, if you wanted to do gender predicts actual and actual predicts the difference, something like that, you can't do that within this framework. You would need to move to a path model framework because actual or ideal each can either be a predictor or an outcome, but they can't be both simultaneously in this framework. So I'm having to estimate a bunch of different models to sort of get all the pieces together because of that limitation. And then one more. Let me go back to the picture here, very top of the handout. So that the variables that we're predicting are people's responses to this figure right here. Are these numbers? Not really. It's ordinal, right? There's a size dimension here, but like, is the difference between 1 and 2 the same thing as the difference between 6 and 7? Yeah, no. So even though um, we are, like, arguably these things are normally distributed, they're not really interval. So I wanted to show you then what we would do to predict these responses as ordinal instead. I just saw it. Here it is. So I set up a model. This is model 6 on page 11 that treated the difference as ordinal. So it works out that there's only 5 different values that the different scores were. I think this one should be a positive one. That's a typo. There we go. People thought that they should be 3 units smaller, 2 units smaller, 1 unit smaller, that they should be fine, 0 discrepancy. Another copy paste error here. Or that they should be 1 unit bigger. So we can treat that difference as ordinal. And does this look familiar to you? Remember this? If we treat the difference score as ordinal rather than interval, we can fit a cumulative logit model. So that is this idea of submodels, where we have submodels is 1 fewer than the number of possible responses. By default, the software fits for these models tends to fit a proportional odds model, which is where the effective gender is the same on every submodel. We don't have enough people really to test that with the gender discrepancy that we have, so I'm going to leave it alone. And here is what it would look like to try and get each of the thresholds for each possible gender, as well as the gender difference. I switched to denominator degrees of freedom none so that SAS and Stata would match. And I end up with this thing right here. The discrepancy between ideal and actual is significantly more negative in women. Same answer, But if you asked me like what to do with this coefficient, I'd have no idea at this point because I have a difference that I'm treating as ordinal, even though the original variables are interval. Like numbers at this point are starting to be like not mean anything. So I thought I would try to fit a multivariate model where I had both ratings in the same model. And you know what I realized? I had never actually tried to do this before. Neither program will let me have separate thresholds or intercepts across DVs. It's the proportional odds assumption comes back to bite you in the ass. So this handout actually took a while to build because I was wrestling through all of these issues. I don't actually have the model that I wanted to have because of this. So when you're fitting multivariate versions of generalized models, you have to be very careful about letting each outcome have its own properties. Each outcome gets its own intercept, each outcome gets its own variance thing that we've been doing. That only works in normal. In non-normal, what I discovered is that you would have one set of thresholds, for instance, that both outcomes or three outcomes have to share. That's no good. You would have you could set up a different effective gender for each outcome via some kind of interaction term, but it would be proportional odds within that. The same thing is true for distributions that have some sort of stretchy factor. Like if I wanted to predict two counts simultaneously, there's no way to tell the software that each count needs a different stretchy factor because everything's in one column. And the fixed effects only differentiate the predicted outcomes, not the stretchies. So this is where I realized that, like, no, multivariate generalized models in univariate software like this, just no. Nope. They're too inflexible. The only way really to do a multivariate generalized model where each outcome would have its own set of thresholds, its own stretchy factor, its own whatever it needs, is as a path model. So like this is just it's not going to work. That's where part one ends and part two begins. I have to I have lecture 5 that we haven't done yet. That this is going to be the punchline to, because the other thing that I have to explain is how you set up an R matrix for two outcomes that aren't normally distributed. So let me go back here just a second. Back when we pretended that this outcome was normal, we're saying that this variance covariance matrix describes our outcomes, right? Okay, we're back in interval normal land, right? We're just going to be like, no, 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 it's fine. They're numbers, I swear. Yeah, delayed reaction. So it's pretty easy to tell SAS or Stata to allow a different residual variance for each outcome, right? We just say it's unstructured or it's heterogeneous variance, whatever, right? And it's pretty easy to say, well, just put a covariance there, right? The residuals between people, the same person or the same family or the same whatever, they get to have a covariance, right? Cool. But what if I don't have a residual variance? Like in a logit model, regular logit or cumulative logit, there's no residual variance, is there? Nope. So how do I make a covariance if I don't have a variance? Exactly. There is a workaround that you can use. It is a random intercept. Those of you who've had multi-level modeling with me will be like, what? It's back. Yeah. The only way to induce a covariance between residuals, so to speak, for generalized models is through random effects, random intercepts. And so that's what I have to explain in order to describe how this is going to work either in multivariate generalized models or in path models. It's going to happen through a random intercept. That's going to take a leap. So that's the next topic. All right. How are we doing? Do you feel like you can do at least one version of the 12,000 permutations I've shown you for your homework? Just one. Again, what I would recommend is the first version, which is one of the reasons it was first. Let me find it again. Keep going. Where's Waldo in the handout? This version. Model 1A. That will lend itself most directly. So we have training group, pancakes or crepes is like gender. We have whether you made pancakes, whether you made crepes is like actual and ideal. So this is one option. The other option is to create 4 outcomes. Like you would have, let me do it for you. You type real quick. The other way that I would recommend doing homework, you can choose which way makes more sense to you. You would have something like actual men, actual women, and then you would have ideal men, stop it, ideal women. And the rest of that would go away. Okay? You could do 4 intercepts. Then the model would give you all 4 means, and any possible difference that you would want is a linear combination. So I would recommend picking one of these 2 approaches. We have not practiced anything related to this one, but there's a sense in which it's more direct because you don't have to do the calculus of figuring out how to get some of the means. They're just right here. So that would be my recommendation, is either of these 2 variants. Okay, questions? Any of that you need to hear again before we adjourn? Okay, so then the plan for Thursday, lecture 5, so I can tell you what the hell a random intercept is, because they're going to start showing up in models for generalized outcomes as a way to get a residual covariance when you don't have a residual variance. That's on tap, and then we get to start path models. Hooray! Has anyone here done path models before? Nope. Have you seen them? There's pictures. You'll like them. It's one of the few areas of statistics where people just abandon equations and just start making pictures. They do. It makes people like my husband crazy because he's like, this is not a model. Like square plus circle is not a triangle, damn it. Like, what is this? So we'll do both. We'll do pictures and equations. To be honest, to write the code for the path models, I almost always make a picture because then the code maps onto it. It's like, okay, this line, I got to type this sentence to make that line. I got to type this sentence to make that line. So graphically, it is helpful, especially in presentations and stuff. But you don't. But what all of the stuff that we've talked about, you can depict as a path model too. So that was part of the rationale why the second half of example 4B And the second half of this example are going to be in path models. And so I've got pictures and equations and code to do all that. So good. Then you'll be excited to finish out the semester with path models. Hooray. And for those of you who are interested in continuing on, now that you know, after this semester, if you know link functions and linear models and path models, you will be ready to totally kick ass in structural equation modeling in the fall. To be honest, the folks who haven't had this class are probably going to be struggling because it's a big jump to go just from like ANOVA to structural equation modeling. Like all the things that we're doing in here are like the intermediate ground, sort of warming our way up. So I hope that you have that. If you can take it, I'd welcome any of you to take that in the fall. I don't know if we'll be Zooming in the fall or if we'll be in person, but I know that I'm on the books for it. So it's a 6249 is the class. All right. Anything else? We're gonna call it a day. All right. Well, I hope we don't have snow, but if we do, stay safe, stay warm, and I will see you guys Tuesday. Let me know if you need anything before then. Okay. Bye, everybody.